Good morning everyone and welcome to this video lesson. This is the third video in a series of videos explaining the discontinuity of the piecewise function in this line. So this is the piecewise function. At the second video, we have checked the continuity at the interval boundaries. We have ensured that the function is continuous at the left boundary a equals to -2 and at the right boundary b equals to 5. However, considering the theorem IVT, intermediate value theorem, we also need to check the continuity on the entire interval. We need to verify that the function is continuous at every point within the interval open boundary -2, 5 closed boundary. So let's read the IVT again. Let a function f be continuous on the closed and bounded interval ab, where f of a is not equal to f of b. Then for any number k between f of a and f of b, there exists at least one number c, which is an element of ab such that f of c is equal to k. Simply put, we need to ensure that for every element c in the interval -2, 5, f of c possesses a continuous and surely defined value. Therefore, it is essential to verify that for each c, which is an element within the interval, the limit of f of x as x approaches c exists and is equal to f of c. Why? Let's describe the implication of the discontinuity and the letter k. If a function is not continuous at the point c, for example, c equal to 1, within the interval a and b, the IVT cannot guarantee the existence of c such that f of c is equal to k. So if f of x is not continuous at x equals to 1 or at c equals to 1, there might be no value k for which f of c is equal to k due to the discontinuity. Hence, the limit of f of x as x approaches to c must exist and equal to f of c for f of x to be continuous at c. And since we're not sure that there's really a letter k because the limit of f of x as x approaches to c does not exist, then the piecewise function is discontinuous. Again, at this point, our task is to examine the elements of the interval and identify where f of x as x approaches that letter c, that point within the interval, is not equal to f of c. So please observe, so our c is 1. And then f of 1, okay, so if x is equal to 1, it's 3, right? Okay. Then the limit of the f of x as x approaches from the left, then that would be less than 1. So the expression to use is for -x squared. Alright, and do direct substitution, the limit is 3. Now computing for the limit of f of x as x approaches to 1 from the right, then that would be greater than 1, right? So the expression to use will be square root of x minus 1. And doing direct substitution, the limit is approaching 0. And the limit of the f of x as x approaches from the left is not equal to the limit of f of x as x approaches from the right. So we can say that the limit of f of x as x approaches to 1 does not exist. Therefore, we can say that the limit of f of x as x approaches c is not equal to f of c. And f of x is a discontinuous function. The reason is IVT. So we are guided by the intermediate value theorem. And the discontinuity is essential. We have a jump discontinuity at x equals to 1, which means that we need to jump from one point to another point of the function in order to reach the other part of the function, right? There's a jump from this point to this point. Alright, so it's GeoGebra time. Let's use GeoGebra to check whether the function is continuous at A equals to -2, B equals to 5, and C equals to 1. So to compute for the limit of the piecewise function as x approaches to -2 from the left in GeoGebra, we're going to use the command limit below. And the syntax will be limit below, then call the function f of x, comma, -2. To compute the limit of the piecewise function as x approaches to -2 from the right in GeoGebra, we use the command limit above. And the syntax will be limit above, then call the function f of x, comma, -2. Since the left hand and the right hand limit as x approaches to -2 are equal, then the limit of the function as x approaches to -2 does exist. So in GeoGebra, to compute the limit of the piecewise function as x approaches -2, we use the command limit, and then just type in limit, then call the function f of x, comma, -2. So use the same syntax for the points when b is equal to 5, the right boundary, and c equal to 1, the x value of the point of discontinuity. Alright, so please observe as I use these commands in GeoGebra. Alright, and let's compute the limit as x approaches to 5. So just change -2 here to 5. Limit below from the left, the limit from the left of 5 is 2. And then the limit of the function as x approaches from 5 from the right. So just type here 5 is also equal to 2. So the limit of the piecewise function as x approaches to 5 is equal to 2. Okay, because the left-hand limit and the right-hand limit of the function as x approaches to 5 are equal. So the limit exists and is equal to 2. Now let's compute the limits as x approaches to 1, which is the x value of the point of discontinuity. So we type here 1. So as x approaches to 1 from the left, and that limit is 3. Okay, and then the limit above. Okay, so the limit of the piecewise function as x approaches to 1 from the right is equal to 0. So the left hand limit and the right hand limit are not equal. So we can say that the limit of the piecewise function as x approaches 1 is a question mark. So since the limit below and the limit above of the function as x approaches to 1 are not equal, then the limit of f of x as x approaches to 1 does not exist and has been denoted in GeoGebra with a question mark. And at this point, I would like to thank the authors of the basic calculus book that I'm reviewing and CNE Publishing Incorporated, and to all of you who are watching the video lessons and reading the teaching documents. So thank you. So this is Tutor Man, and please feel free to recommend me for tutorials as a vocation. So thank you again for watching, and I hope that you have learned something.